So that's the chapter 5. And the chapter 5, I believe the textbook have a different title, but basically that is just regarding the time domain. Categorizations of control systems. We call control system basically is a dynamic system. Okay, so here the tools are available here. Okay, so control or dynamics. The big concept is this. For this, you wouldn't be able to see from any textbook. That is my comprehension, my own comprehension of the dynamic systems. So consider a block diagram of certain dynamic system. And for these dynamic systems, we have initial conditions. Okay, so you could imagine is like this. For example, we consider x double dot plus 2x dot plus 5x. Not too close. Give yourself more space here. A few minutes. Okay, so we consider this case. Okay, so we consider this one. So basically, this one in terms of the language using in vibrations is something like this. So here we have a unit mass 1 and 2, and here is 5, and here we have the force vibration Ft equal to 2 times sine t. Okay, so this is what you are familiar with. Is we call the force vibrations, basically force harmonic. In particular, is the harmonic vibrations here. Okay, so here we have the initial conditions. For example, initially we give as 1, and this one equal to 0. And also we have the signal input is we call the command. Command basically is our force, external forces. Okay, so external force, that is the language using in vibrations here, just like this f of t. So for all the dynamics, it will take up the two kind of informations. For this, as one example, basically here is this. We hand a mass to this one, just hand there, and we just hand there and let the gravity to take equilibrium with the spring. So this one will kind of deform the spring a little bit downward, and that is the equilibrium positions. And all the vibrations, the degree of freedom, we define the degree of freedom x of t. X is measured from its equilibrium positions. You know that one. So for this initial condition, how we set up, basically here is this. We simply, upon the equilibrium positions, we drag this mass block by 1 unit, hold there. And then once we start it, we just release our hand. Okay, so that means the system will go back. In addition, we have command. We given this force excitation. So that is this force will be there perpetually. So that is things. So for this one, for the initial conditions, it's going to influence the dynamics, and the command will influence the dynamic systems. The initial conditions will influence dynamics and to come up with the transient response. the command or the force excitation we'll come up with is the steady state response. The transient response is only happened during the transient time, just like here I'm drawing here. So those are the transient response. Eventually, the transient response will be gone. Okay, just like here, there's a transient, there's a transient. And let me call the transient response is using YT. And this one, let me use YSS. So the total response basically is governed by YT, the transient, and plus the steady state response. Okay, so in terms of the language learned in differential equations, this is called the homogeneous solution. This is called the particular solutions. Okay, so that is the concept here. And for this is one example we can try to see what's going on here. So we can try to solve this one quickly. You can take Laplace transform. After the Laplace transform, this one can be equal to S. Okay, so earlier we have practiced is we always ignore the initial conditions, but here we try to involve the initial conditions. So here we can introduce this one equal to 1, and this one equal to 0, this one equal to 1. Okay, so plug in those things carefully. Eventually you will obtain is, let me ignore a few steps. The solution will be equal to, we've been tested for a few times, we can drop it. But okay?
Yeah, if you don't know this, you failed vibrations.
So with these things, let me use a little bit anatomy here. This is during the solution process, you can see the detail. But here we have two parts. This is the transient response. This is the steady state. And why? I believe this is from homework, from test. You can see the transient response should look very, very familiar, right? It always, for this example, that is certain some oscillations have the amplitude that is oscillated under the envelope of exponential decay. So for this one, for the transient response, we have it's like this. Whatever we combine, that is in the oscillations of the sinusoidal functions, and they may have the phase angle, and But anyhow, QD should be faster. Let me change the drawing. Okay. And again, sorry. So that is our system here. So this is the period of oscillations, or we can say the oscillation frequencies. What is oscillation frequency here? That is this one, right? So that is the frequency of oscillations. And again, here when you do the detail, you can see where it comes from. But again, if you put into the standard template, what is 2? Is 2 equal to this? I'm asking you, this is the frequency of oscillation. Is that equal to our natural frequencies?
No, I thought that was WD.
Is this one?
I thought that was.
No, right?
It must be WD.
So,
WD is equal to this. W1
yeah.
times the square root
So
of
this
1
one,
minus
in terms
theta.
of right now I'm transposing. So this one should be equal to omega n times this one, right?
Yeah.
And that is what I call defined as the challenging questions in our test. Okay, so as long as you can catch up this concept, then even you have certain mistake, you should be fine, and not many. But again, this one is not only from, if you haven't taken the vibrations, that's okay, because we have been talking from a different viewpoint. For example, this is our complex plane. And say if this is the location of the pole, and here that is the frequencies, and here is I define as say this is imaginary part, and here is the real part, right? Yeah. And I remember I've been telling you this amount is equal to this one, yeah. Right? And then
that's what
here this angle is from here is
cosine.
A cosine.
Yeah.
Zeta. So this amount is zeta times omega n. Right. And this is exactly the imaginary part is governed the vibrations, and the profile is governed by the real part, the real t, the real part of times t, right? Okay. So again, from that problem, I try to see whether you'll be able to integrate. You have learned from both classes about this one. Okay, so we're back to here. So basically, right now you can see this is oscillation, and oscillation has an amplitude. Amplitude is governed by exponential decay. So eventually, this oscillation will be going to 0. So for all the signals, if they eventually going to go to 0, and for the stable system, we call that the transient response. So this is a transient response. For the steady state response, and here you can see is the time. And let me draw our signals. Our signal is 2 sine t. Again, here the signal is oscillating slower than this one. So here I draw it slower. Okay, so here is peak equal to 2 here. So this is our command. For this one, we can do quick calculation here. So this one will be equal to, if you do the calculation, the amplitude will be equal to 5 of square 5 times sine t plus certain phase angle here. So the amplitude here is this one. So let me draw the amplitude will be something like here. Okay, so the amplitude here is square 5 over 5. And then the oscillations, here, the oscillation is at the same frequency of 1 here. Okay. So here for this case, for the system, its frequency eventually, if we superpose the two signals together, then you can see initially the signal might have certain random, kind of a random or like a vibration, but eventually the signal is going to follow up the frequency of the command. Eventually the system will be oscillating at the frequency of 1. Although its amplitude is not able to catch up the given one, but this is an open system. Okay, so in general, this is the more general process. When you're given the dynamic system, you consider both initial conditions and the command. And here we, from your vibrations point of view, you want to know is the total response, is the total solutions of the system response. And here you have to consider initial and the transient response and steady state response. Yeah. For controls, if you remember, when we define the transfer functions, if you remember like lecture notes, when we define the transfer function is based upon which we assume the system initial conditions is 0, which means the transfer function only is to study the steady state response of the system. For transfer functions, we don't care about the initial conditions. We don't care the influence of the initial conditions. So which means for the control systems, what we are concerned most of the time is about their perpetual response, perpetual behavior. As far as how they approaching, how they transient behavior will be, is not our concern in the control system most of the time. Okay, so here from the beginning, we build up the block diagrams. And again, this is a very important concept. And in block diagrams, we don't consider the influence of the initial conditions because those influence will be gone. It's only a short of time influence. Eventually, it will be gone. So here for our block diagrams, and again, for system dynamics, in terms of control language, we don't consider this route. This route will be just be eliminated, will be die out in short of time. Okay, so following up in the control system, we more concerned is about this route. And this route, what is the steady state response to the command? Basically, that is our transfer functions. So, for example, here, if say, let me say this steady state response, let me define as the y, and so say that, for example, here I would say the y as and for example, command is r of t, so here is r. So basically, this is our transfer function. Okay. So here for this kind of plugin, I just want to again one more time to impose the concept of the transfer functions. And so later on in chapter 5, we will be more on this route here. And in this route, instead of in the S domain, and we have done quite a bit of exercise of doing the transfer function analysis in the S domain. So in this chapter, we will do the same thing, but more or less will be in the time domain. And then the big picture is this. We're going to study how we analyze the time domain categorizations of the steady state for two systems linear order system and second order system at most. And linear order system would be more like not like here. I couldn't say that one. Okay, and we will only use up to second order system. That pretty much is the same as you've seen in your vibrations. And as far as for the higher order systems, and in the end of this chapter, I will give you a technique. You'll be able to approximate any higher order system down to the second order or lower order system. Okay, so that is the goal. Okay, we stop here today. Thank you.